Let's talk about section 9.6, momentum and collisions in two dimensions. Remember that momentum is a vector quantity. That means it's got a direction. And so if we've got motion in two dimensions, like the billiard balls shown in the image here on the slide, the momentum is got a direction as well as a magnitude. And just as with everything else we've done, we can treat each component of those things independently. That means the x component of the total momentum is conserved and the y component of the total momentum is conserved, because I can't have a force acting in the x direction on something can do nothing to the vertical momentum of it. And this is basically the same reason why the motion of things, the x motion and the y motion, are independent. All these things that go all the way back to chapter 3 and that demonstration where we shot a ball and dropped a ball and they fell together. It's the same general idea. If I push in the x direction, I do nothing to what's going on in the y direction. So the momentum is conserved in both components independently. So what that means, in section 9.5, we did a conservation of momentum problem that was all in the horizontal direction, and so we just had that one component we didn't need to worry about. But if we've got motion in two dimensions, then basically we have to take a look at the component of the motion of each object in the x and the y directions. And so the example here of one bird attacking another bird, the larger bird is coming in at an angle from the horizontal. The smaller bird is traveling in the horizontal direction and they collide, so they become one massive object. The momentum of that new combined bird has to equal the sum of the momenta of the two birds beforehand. And beforehand, there was momentum down and to the left, and there was also momentum straight to the left. And that means that the new momentum is the sum of that. It's still going to be to the left, but it's also going to be somewhat down. So we won't worry about going through the example problem that is worked out by the book. We'll just do our own example problem. In this one, we have hockey pucks on, well, air hockey pucks, where we're neglecting friction. They each have 100 grams mass. Prior to the collision, puck 1 travels in a direction that can be considered the plus x axis at 1 meter per second. So remember, with a conservation thing, we sort of have a before and an after. So our before picture, the problem tells us that puck 1 is traveling in a direction that can be considered the plus x axis, and puck 2 is traveling in the minus y direction, and they run into each other. So I drew puck 2 up here. Here's 2, here's 1. It's traveling in the minus y direction. So V1 initial is 1 meter per second to the left, and V2 initial is 2 meters per second down. So I'm going to call that minus 2, and it's really in the y direction. I can see that from the drawing. If I were being super careful, I would write it in the subscripts that that's just in the y direction. After these two things, then they collide. They collide. After the collision, puck 2 travels 30 degrees above the x direction at 0.8 meters per second. 30 degrees above the x direction. So V2 final, and it's at 0.8 meters per second after the collision at this angle as indicated. And the question is, what is V1 final? And that's a vector. What is the magnitude and velocity, the magnitude and direction of the velocity of puck 1 after the collision? Pure, simple conservation of energy. There's no external forces because we're neglecting friction. So momentum is conserved. So that is expressed in the most generic way as delta P equals 0, which means P final minus P initial equals 0, which means P final equals P initial. Okay, super general vectors. So that means that P final x is equal to P initial x, and P final y is equal to P initial y. Okay, that's the total momentum in the x direction after the collision is equal to the total momentum in the x direction before the collision, and likewise for the y direction. So my general statement has now become general vector statement has now become two scalar equations. Let's go ahead and write these things out. Pfx, the final momentum in the x direction, is equal to Pix, and let's expand that. The final x component, x momentum, is m1 v1 fx plus m2 v2 fx. Okay, I'm expanding the left-hand side. Now let's expand the right-hand side. m1 v1 ix plus m2 v2 ix. Okay, I have two objects. I haven't put any numbers in. That's the next step. This v1 fx, that's one of the numbers I'm looking for. The problem tells us that m1 equals m2, so, and that's equal to 100 grams. It's going to be confusing if we put that 100 in there. I'm just going to call this m. Okay, we don't need a 1 or a 2, so they're all the same mass. And the reason you're going to do that is, see, once I just put that m in there, they're all going to cancel out. So m times v1 fx plus m v2 fx, if you look at your diagram up here, my diagram for after the collision, the x component of v2 after the collision is 0.8 cosine 30. This is the thing that I told you way back on the first day of class needed to be automatic. When you look at this diagram here of that velocity vector where you've got a magnitude and the angle, the x component of that is the component of the vector v2f in the x direction, which is adjacent to that angle 30, which is cosine of 30 times the magnitude of that vector. So that's the left-hand side of that equation. m1 v1I, well, v1I is that 1 meter per second, so that's just m times 1, and v2ix is 0 because it's traveling initially only in the y direction, not at all in the x direction. So notice I've got an m in every term, so I can cancel that out, and that gives me v1 fx equals 1 minus 0.8 times cosine of 30 degrees. So v1 fx equals, let's get that number, 1 minus 0.8 times cosine of 30 degrees is 0.31 meters per second. So now I have the x component of puck 1 after the collision at 0.31 meters per second. I follow the same argument for puck 2, sorry, for the y direction, m times v1 iy plus m times v2 iy equals m times v1 fy plus m times v2 fy. I'm not sure if the words that I was saying match the letters that I was writing. Also, I just realized on the previous page I wrote final equals initial. Here initial equals final. It's all the same anyway. The masses all cancel out. It is this thing that I'm looking for, v1 fy. What's the initial y component of puck 1? 0. What's the initial component, y component of puck 2? It was -2. 0 minus 2. I'm canceling the m's out already. Equals v1fy, the thing I'm looking for, plus v2fy, automatic. I look at that vector drawing there, and the y component of v2f is v2f times sine of 30, or 0.8 sine of 30. It's pointing up, so it's positive. So that gives me v1fy is -2 minus 0.8 sine of 30. v1fy equals, let's see what that number is, -2 minus 0.8 times sine of 30 degrees is -2.4. Does it make sense that it's a negative number? Yes, because initially everything was either moving to the right or moving down. So at the end, I know that puck 2 is going up, but my total momentum has to be going down. So if puck 2 is going up, puck 1 has to be going very down so that the total momentum is still in the down direction. In any event, I now have v1fy, v1fx from the previous page was 0.31 meters per second, positive. The total speed, v1f, is the square root of v1fx squared plus v1fy squared. So v1f is square root of the square of those two numbers, 2.4 squared plus 0.31 squared, and it's 2.42 meters per second, just a hair bigger. This number's, the 2.4 is so much bigger than the 0.3. When you square it, it's way bigger, so it's not that much larger. In fact, if we round it to two significant digits, that 0.31 doesn't make any difference at all. So there's your final speed. What's the direction? Let's sketch this vector. v1fx is in the positive x direction. v1fy is a big vector in the negative y direction. So here is our vector v1f, and this angle, theta, is the inverse tangent of opposite over adjacent, v1 fy over v1 fx. So that theta is equal to inverse tangent of 2.4 over 0.31. And that's 82.6 degrees. So that's our direction. It's about 83 degrees below the horizontal, below the positive x direction. So the basic principle here, though, is just you can treat the conservation of energy, sorry, conservation of momentum in each component of the direction independently. You just have to do it all the way through for all the objects before and after.